15.8 talks about triple angles in spherical coordinates. So in spherical coordinates we have rho, which is a fixed length. We have theta, which is the same theta. And phi. Phi equals 0 starts on the positive z-axis, and that's the positive rotation. So if I mimic r, that's x. I don't like that one that much. Let me fix that again. There's y. And this is really z. So a couple of things to notice. Rho squared equals r squared plus z squared. And r squared we know is x squared plus y squared. So rho squared equals x squared plus y squared plus z squared. If I look at this triangle, I'll notice that cosine of phi is the opposite, and the opposite right there is really r, over the hypotenuse, which is rho. If I cross multiply, I'll notice that r equals rho, the cosine of phi. One tiny mistake. Cosine is not the opposite, guys. There's the right triangle. Cosine is the adjacent over the hypotenuse. So if I cross multiply, z would equal rho the cosine of phi. Right there. And lastly, if I look at this triangle, if I look at the sine of phi is the opposite over the hypotenuse. If I cross multiply, r equals rho the sine of phi. But I know that x is r times the cosine of theta. Well, if I know that this is rho sine of phi, that will get me this. And I know that y is r times the sine of theta. And if I know what that is, these are my formulas. Now here there's a catch. Phi could start on the positive z-axis, and it could run as most pi units. It can't run more than pi radians, because then you'll start overlapping, and that's not something that we do at all. This is not preferred at all. So first batch of the problems, let's go back and forth. Let's plot this point where spherical coordinates are given. So these are spherical coordinates, and they always go in that order: rho, theta, and phi. So I'm going to rotate 3 pi over 4. I am lining up 45 degrees in the second quadrant. Phi is going to run down 45 degrees, and you're going to move 3 units. Oops. You're right there. That's the location. This is rho, and if I want to go to my equivalent rectangular coordinates, x, y, and z, well, let's see how this works. I start with, and those are a bit lengthy, I start with z. X equal rho the cosine of phi. That is 3 the cosine of pi over 4. That is 3 radical 2 over 2. Let me see, why am I not liking that as, oh, I'm sorry, that's not x. That is c. Okay, much better. Oof. So z is 3 radical 2 over 2. Okay, very good. And what is y? Well, what is x? X is rho times the sine of phi cosine of theta. That would be rho, which is 3 cosine of theta, 3 pi over 4, times the sine of phi. Phi is pi over 4. So this is radical 2 over 2. This is negative radical 2 over 2. And this is a 3. So that's a negative. And this will be a negative. If I multiply those, that's negative 3. 2 over 4 is that. That's 3 halves. And if I want to find y, let me just give myself a bit more space. If I want to find y, I will say y equal rho times the sine of phi sine of theta. So that's going to be 3 times the sine of 3 pi over 4, which is radical 2 over 2, times the sine of pi over 4, radical 2 over 2. So that is going to be 3 halves. That's the equivalent rectangular coordinates. You'll notice this is very beneficial if you have an actual sphere to use the triple integral and find the volume, but the work is intense. And the same deal here. The main point for me really is for you to plot it, see where that is. Converting is a good practice. So what do? Again, this is rho, theta, and phi. Start with theta. Rotate to 5 pi over 4. You're lining up halfway through that quadrant. Phi is going to run down from the top only 30 degrees. So you're along that path. And you're going to move 1, 2, 3, 4 units. You're right there. There you go. And to convert that, again, start with, well, we could say x is rho times the cosine of theta. Cosine of 5 pi over 4 is negative radical 2 over 2. Sine of radical of pi over 6, which is 1/2. So that is negative radical 2. Y is 4 times the sine of 5 pi over 4, radical 3 over 2 for the sine of phi, and that turns out to be a negative radical 6. And z is the simplest because it's only rho times the cosine of phi, pi over 6. That is 4 times 1/2, that's a 2. So move negative 2 in the negative radical 2 in the x, negative radical 6 in the y, and up, and there you are. Alright, what if I gave you x, y, and z, and I want you to go to rho, theta, and phi? Well, let's see how that works. I know that rho squared equal x squared plus y squared plus z squared. That's 12. So rho is actually 2 radical 3. And I know that x and y are actually 2 and 2. That makes theta pi over 4 because I'm in quadrant 1. And to find phi, I could use z specifically. That's very wise. Z equal rho times the cosine of phi. This is 2. This is 2 radical 3, which is rho. Cosine of phi. So cosine of phi equals 1 over radical 3. And phi will be the inverse. Those are normally standard angles, but since I picked them at random, so I should have picked them differently. That's not a standard angle. Or is it? Yeah, it is. It is. Cosine of which triangle gives me 1 over radical 3. There's 30 degrees. 1, 2 radical 3. Cosine, oh no, it doesn't work. tangent will give me 1 over radical 3. So yeah, I messed up on that one. That's okay. So we could say the inverse cosine of 1 over radical 3. Again, those are normally standard angles. I made those up, and that's why they're not working accordingly. How about this? Given this rectangular x, y, and z, let's see how this works. First, you start with rho squared equal 1 plus 3 plus 4 times 3. And that would be 12, 16. So rho is 4. Very good. Theta. If I take the x and the y, I am moving -1 radical 3, which indicates I have a reference angle of this is a 2, of course, for this to work. I have a reference angle of pi over 3, and I would like to know in the spherical quadrant is 2 pi over 3. Got it? And again, I use z to find phi. That's very wise. Z is 4. Z is 2 radical 3. Rho is 4, the cosine of phi. So cosine of phi is radical 3 over 2, and I know where that is. Cosine of phi will be radical 4 over 2 at pi over 6. So again, a bit more work than polar, and the calculus is really intense. I'm leaving that for next class meeting. Can you try and get an idea of what these graphs look like? So think about it. Describe, well, I'm going to graph. Rho equal A. If rho equal A, I could go A. Now, phi runs up and down, but theta rotates all around, creating a sphere with radius A. How about, okay, how about if I let theta equals A? Let's say A is fixed to be along that angle. Now first, a rho could go extend as much as you like, and phi could run back and forth, creating really a plane. Only in that one direction, whichever A is, because rho cannot be negative. So you get a plane, but it's only going to cover one of the quadrants. What if I let phi equal A? If I fix phi to be a specific angle, let's say right there. Now, rho could run from 0 and run all the way up, and if theta rotates all around, you create an infinite cone. Okay. Describe, what do you think this means? Well, if I factor this, I see that I messed up. Amending that, again, I forgot this is not R. You can't just choose any numbers. So this would be either a sphere with radius of 3 or radius of 1. So those are two separate graphs. And if I was to say, what is that the graph of? Well, we know how that works. If I multiply by rho, I'll get rho squared equal twice rho the cosine of phi. That is x squared plus y squared plus z squared equal twice, and that's z. So x squared plus y squared plus z squared minus 2z plus, take half of the middle number and square it. You're looking at x squared plus y squared plus z minus 1 squared equal 1. We know what that is. That is a sphere centered at 0, 0, 1, and you go one above, one below. Something like this. So either you graph it or you tell me exactly what I just said. This is a sphere centered at 0, 0, 1 with a radius of 1. That would do the trick. And if I was to go ahead and look at convert the equation to spherical coordinates, okay, well, spherical coordinates, that is rho cosine of phi, that is rho cosine of theta sine of phi squared plus rho sine of theta sine of phi squared, rho cosine of phi equal rho squared cosine squared of theta sine squared of phi plus rho squared sine squared of theta sine squared of phi. And you notice this is going to always happen. I could factor a rho squared sine squared of phi out. I'll have a cosine squared of theta plus sine squared of theta, which is a 1. So I'm left with rho the cosine of phi minus rho squared the sine squared of phi equals 0. Factor a rho out, cosine of phi minus rho the sine squared of phi equals 0. Rho equals 0, or cosine of phi minus rho sine squared of phi equals 0. So rho equal, if you move it over and divide by sine squared of phi, there it is. You could even massage that a bit and say that's cosine of phi over sine of phi times 1 over sine of phi, which is cotangent of phi, cosecant of phi if you wish. If I want to sketch these graphs, let's see how this looks. A rho is between 1 and 3. It's that piece. Theta is going to run between 0 and pi. Between 0 and pi. So phi could run all the way down. And theta runs back and forth. So probably, okay, I get what the graph looks like. Here, it's easier to go the other way around, which is, now that I know what it looks like, between 1 and 3, and I'm gonna get another one. Okay, something like that. Like half an avocado without the actual seed, the right half. And if I am to look at part B and look at the graph of that and what it looks like, I'm looking at the phi runs from 0, okay, from pi, so I am below, and rho runs from 0 to 1, and theta runs all around, so a circle with a radius of 1, and a circle with a radius of 3, and again half an avocado, but it's now laid flat, and that's what it looks like. So it turns out the calculus here looks a bit messy. This is provided in your test. You don't have to memorize that. X, Y, Z, dV picks up a rho squared the sine of phi d rho d theta d. So what you have to do is just go back and forth, sketch the solid, so you notice this has no consequence. We're looking at phi runs from 0 to pi over 4. So phi runs from 0 to pi over 4. It stops right there, about halfway through. And we notice that theta runs from 0 to pi. If theta runs from 0 to pi, it's going to run all around, which means right? And phi and rho runs from 0 all the way to 2 the secant of theta. What does that mean? Well, rho equal twice the secant of phi. If you multiply by rho both sides, oh, take that back. You need to. Rho equal twice the secant. I thought it was the sine. So rho equal 2 over the cosine of phi. Rho cosine of phi equal 2. That means z equal 2, which means you go up 1, 2, and would be, let's say that's the 2 right there. So we're talking about that half of a cone. And if I look at my last example, evaluate the integral by using spherical coordinates. Alright, we want to really review what we're doing. This is going to be the integral. Well, this is simply rho squared, and dv is by itself rho squared sine of phi. That's provided on your exam. You don't have to memorize it. Okay, so let's see what they want. E lies above the cone. There's the cone. And between the sphere z equal 1, so rho squared equal 1, or rho equal 1 and rho equal 3. I see. So a sphere that's running between, okay, so you have two spheres. And what you're doing, you're cutting and rotating all around. And you're going to end up with two of these cones. Well, not a big deal, because when you look at this, you know rho is going to run between 1 and 3. That takes care of it. So now if you're looking down, well, if this is at 45 degrees, that's very easy to figure out, because that's what this cone is. Cutting the quadrant exactly in half. And theta is going to run all the way from 0 to 2 pi. And that will take care of it. And that's pretty much it for this section.